Welcome back. It is lesson 11C. Can you hear me now? In 1959, and that did the streak. In 1959, Arthur C. Clarke predicted a personal transceiver so small and compact that every man carries one. Every man and woman carries one. The time will come when we will be able to call a person anywhere on Earth merely by dialing a number. It took over 35 years from when the concept of cellular phones emerged in 1947 for the technology to be commercially available in the United States. By 1987, telephone transcribers exceeded 1 million, and the airwaves were crowded. According to a Pew Research study in 2013, over 90% of American adults owned at least one cell phone. Part 1, make a quick sketch of a graph that you believe shows the growth of cell phone usage in the United States. Remember, time is probably going to be in your x-axis, and then the growth of the cell phones will be on your y-axis. Hit pause, do a quick sketch, even go on and read through some objectives and some more pieces of our information. Keep going with some questions, and then come back and we can work on these together. The answers you got on question 1 can vary. Now we're going to move on to the objectives. We're going to understand that a change in a parameter of a logistic model changes the shape of the graph and the output. Initial population, growth rate, and carrying capacity are the parameters of the logistic model in this lesson. It's a good thing to write these down, start some flashcards, but initial population, growth rate, and carrying capacity, those are our parameters. We're going to be able to explore the changes in the values of these parameters of a logistic growth model and describe the effect when those changes happen. The curve that best models the growth of the deer population on Smith Island is also the curve that best models many populations that grow to some limit, and this curve is used in biology and in chemistry and in many other fields. It is also very useful in advanced statistics. From the previous assignment 11C, you know that the growth in cell phone subscriptions is slowing down. In a previous lesson, you were working with a recursive model in which you had to know the previous population value in order to predict the next population value. Wouldn't it be more convenient to be able to jump ahead several steps into the future without calculating all of those steps in between? An explicit equation allows you to do just that. You can substitute any input value and calculate the corresponding output value, and you have used this method many times with linear equations. The explicit form of the logistic model is shown in the spreadsheet in the image below. And A, B, and C are parameters for the equation. We're going to graphically investigate the effects of changing these parameters. Make sure you note C. Make sure you see where, make sure you know where A is. I'm going to work on my alphabet next. And make sure you see where C is, and then where B is in the exponent, which is in the denominator. Remember, it's a good time to hit pause, go open the spreadsheet it's referencing, and you do your work, and then come back and we can work on this together. It does ask us to open spreadsheet 11C, and this is in my math lab under spreadsheets, lesson 11C, and go for the one that says in class. Take a moment to familiarize yourself with the graph and sliders, and I have a few pieces missing, so let me fill in the blanks that say A is worth 200, B is worth -4, and C is worth 25. The first thing they ask us to do is to label the horizontal line at y equal 200 on the image above as an asymptote. In this case, the line represents the carrying capacity or maximum value of 200. Notice that the curve approaches the horizontal line but does not seem to cross it, which is the basic idea of an asymptote. And here's what they're asking for that was above, and right here at 200. Y is 200. They're asking us to look at that as the carrying capacity, and notice that our blue curve does not go past it. It gets closer and closer and closer, but does not touch it. Moving on to part B, it says use the slider to change the value of A, the value that's shown in cell D1. Watch the changes to the curve as you do, and how does the value of A, going up and down, affect the shape of the curve? Write your conclusions in complete sentences. For example, one sentence might begin with the phrase, as the value of A increases from 200. Another sentence might start with the phrase, as the value of A, oh, I read it wrong, as the value of A decreases from 200. And another sentence might start with, as the value of A increases from 200. And a third sentence might summarize your findings. Before you look at this, go ahead and make a prediction as to what you think A is going to cause the graph to do. Notice that A is in the numerator. And so I'm going to come up here to the slider, and the phrase was as A decreases. So let's go ahead and do that. As A decreases, hopefully you've already made a prediction what you think the blue line is going to do, the curve. So as A decreases, as A, the red line decreases, what's happening to the blue curve itself? And then you're going to go write a comment about that. Now I'm at 80, heading back up to 200. My A, my carrying capacity, is increasing. Sorry, my population. And then now I'm looking as it increases, or is it the carrying capacity? So looking at A, that looks like the carrying capacity, and as it increases, what does my blue line stretch out to do? Make a note what you're seeing, and then let's go to the next part. Well, first, something you may have written is, as the value of A decreases, the carrying capacity, sorry about confusing you on that one, decreases. And as the value of A increases, the carrying capacity increases. The value of A determines the carrying capacity of the population and is the maximum value of the curve. So now they want us to put A back to 200. And then they're asking us to use the slider that controls the value for B. Watching the curve as you do so, and notice how B affects the shape of the curve. And notice that B is the exponent in the denominator for the fraction x over c. So watching B, right now it's at -4. Let's let it go down. And what is happening to the curve? Notice what that S is doing on the curve as we go down. Now let's let B go back up. Let B be going up, and watch the ever so slight movement of the curve. What is happening to the curve as B gets larger? Look at that. Look at the curve as B gets larger. It's flattening out into concave or convex, as you have learned. Some of you talked about it being parabolic. And so one comment they make after you write your comment is to think that as the value of B decreases from -4, the curve rises more sharply. The rate of increase initially is greater. Also, you could write like, as the value of B increases from -4, the curve rises more slowly. The rate of increase initially is lower. The value of B determines the rate of the increase in the population. B is the rate of the increase in the population. So they're asking us to go back to -4. We're going back to the preset parts. And then finally, it asks us on part D to use the slider that controls the value of C, watching the curve as you do, and how does the value of C, and notice where C is in our formula, it's in the denominator of the denominator. And they're asking us, how does the value of C affect the shape of the curve? So let's go down first. Watch your blue line and see what it's going to happen when our D, whoa, when our C, I'm so sorry, when our C, oh, it just didn't like that. So when our C is getting less, it's decreasing, it's going down, our line is pulling up to the left. But now let's let our C increase, and it's stretching across the X. Watch that green dot. That center is stretching, I'm so sorry, stretching across the graph. And so write something about what you just saw, which could include, as the value of C increases from 25, it takes longer for the curve to begin to rise exponential. The inflection point, if you have not written that down, our green dot is our inflection point. It's greater. As the value of C decreases from 25, the curve begins to rise more quickly, and the inflection point decreases in value. Finally, part E, what significant change in the shape of the curve seems to happen at the large point? That is, how are the two portions of the curve to the left of this green dot and to the right of this green dot, how are they different? Write down some of your observations, and they may include the large point is the inflection point, and it is the place on the curve where it changes from increasing at an increasing rate to increasing at a decreasing rate. And as you investigate each of these three parameters on part F, describe what happened to the large point. And so you might write down something like, the point representing the inflection point is always, write down, the inflection point is always 1/2 the way between the lower and the upper asymptotes, lower being 0, upper being our limit, our carrying capacity. As the curve rises faster, the point moves to the left. As the curve rises more slowly, the point moves to the right. We are now moving on to question 3. If you haven't hit pause, this is a great time to do it, and I'll see you at question 3 momentarily. Finally, question 3. The number of deer on a fixed space, like an island, will likely, very, very likely, have an upper limit. A logistic model is appropriate. The population will grow slowly as it reaches that upper limit, which we are calling carrying capacity. The logistic model does not work as well for the number of cell phones in use in the United States. In what ways is the logistic model appropriate for the deer population, and in what ways is the model less appropriate for the number of cell phones? Talk to the people around you, call somebody, text somebody, talk through this, and write down a couple of thoughts on both of these questions for part 3. And some of the things you may have written are, Smith Island is a fixed space, a fixed area, and the number of deer will grow, but they're constrained by that area. The United States population is changing in size, but the demographics of that population, it's also changing. And as young people grow to an age where they get a cell phone, replacing the loss of older people less likely to have a cell phone, this could happen. Also, we're not bound to a maximum of 1 phone per person. So people who don't even own phones could be being replaced by people who are going to own phones. And then not only might they own just one, but there's no maximum. You can own as many as you want. So even if we maxed out on population, we could continue to increase the number of phones. Thus, unlike the area of the island, the upper limit for the number of cell phones in the United States, it can keep getting moved up and up and up. This concludes our lesson 11C. And with this conclusion, you need to go look at your syllabus. And on your syllabus, you need to determine if you have more to do for this week's deadline, or if you're due for this week or done for this week's deadline. Just make sure you complete all the previews and the practices for this week before Friday night.